Hello, welcome to Anson Griffin's occasional series in YouTube tutorials. Today we're back to one of my favourites, Matlab, and we're looking at a rectification of an oblique image. So if you're completely new to it, we have that image obliquely and we wish to rectify it so that it looks something like that. Okay. So parallel lines are parallel. Now, if you've stumbled across this YouTube video, I have done it in Matlab myself using the Matlab commands, which are a little simpler than that is done here. And the first thing up to say, just where the mouse is pointing out, again, as I clearly say, Mr. Denweiler, he did this, and I want to give Mr. Denweiler the full credit. It's not my work. Okay, so we have the 4-point algorithm, and we're going to do we're going to follow a certain algorithm, and it's a reasonably complicated way of doing it, but it gets a fairly good result. And I'm not going to go through it exactly line by line, because you would need to know some linear algebra, and you want to have an idea of matrices and what homography is. So it's not for the absolute beginners. Although that said, the code is there, and the code is also available from there. You can cut and paste it yourself. So just to comment about that myself. Okay. So I've ran the code and I published it to Microsoft Word, which by the way you can do in Matlab 2007, but not in later editions for whatever reason. Okay. So we've read in the image. Which is floor. Okay. And to solve it, we're going to run this algorithm here, the 4-point algorithm for a planar. Okay, and we're going to use singular value decomposition, and we're going to normalize the homography. And by the way, I took this, again, not my work, I took this as a screen grab from a Google book in Invitation to 3D Vision from just a geometric models. So we're going to follow those 3 points, 4 points, whatever you want to call it. So go back to where we are. So the images that I used are from Hartley and Zisserman, and the images in that book are freely downloadable at this website here, robots.ox.ac.uk. So again, if you're into computer vision and you're into Matlab and anonymous functions and JPEG and all that stuff, the robot site there is a fairly handy site. So I've read in the image, I've made it grayscale, I've got the rows and I've got the number of columns, and I've converted them there into column matrices, and I've displayed the original image. So there is, just go down here, there is the original image. Okay, that one there. Okay, now x1 are the points. So we've got 4 points in the oblique image, and again I've put it into homogeneous format. So in other words, the third column, for want of a better word, is ones. Okay, and if you don't know this, sorry, you just have to go off and find it in some other YouTube video. But to get this to work the way I'm doing it, it needs to be in a homogeneous form. The points in the planar, in other words, when you're looking at it, there's no distortion due to perspective. The corresponding XY, or whatever we want to call it, is here. We then called Mr. Denweiler, wrote a fairly sophisticated function, may I say, 4-point. So I'm just going to go down to that. I cut and pasted that in there. And again, just stating it's not my work. Declare the function. Check that there's an equal number of points. Check that there's at least 4 points. Build a homography. Now, I'm going to post another YouTube video which does this in a much simpler manner, but we're going to do is using a cross product, and we're going to use the Kronecker cross product. Now, I don't know what version of Matlab that people may be running. To get the skew here, when Mr. Denweiler wrote it or used it, I think he was using the inbuilt skew from the statistics toolbox. That wasn't available on the version I was running, so I looked up on the file exchange. I found a skew matrix, so I got that from there. So just to give full credit, excuse me. So I've got I've in that for loop there, I've built up my my DLT, my direct linear transform, for the 4 points. There I've got the SVD, singular value decomposition. I got the column to the smallest singular value, that'll be the last one, V, made it into a column, reshaped it into a 3 by 3, and then I normalized it by dividing by the second singular value. You have to do a check here to see that whether you use H or minus H. So we ran through that here, and then, so in other words, if they're all negative, because every time it's negative, fix comes fix, you've bumped up fix by 1. So if fix down here equals 4, you're going to make the homography matrix, you're going to make it a negative one. So you've got the homography there. Go back to where we called it up in the main one here. There, so we've got H. We started to run it there. We got the locations at the new points. In other words, we're trying to twist the distorted matrix, the perspective distorted image, I should say, into a non-distorted one. So I'm just going to slowly just give you a chance to read that, and I draw it there, and there's the reshaped image. Okay. Now if you're doing this yourself, I was running this on a dual core AMD, and the run time was 2 minutes, 2.5 minutes. So you may think when you run this yourself that there's a fault, but and oh, by the way, and there was a 4 GB RAM. Now that'd be so you'd be using 3.5 GB, and I had everything else shut down. So it is quite computationally intensive. Okay, so hope that helps. Thanks very much.